Okay, so let's talk about gas stoichiometry. Now, stoichiometry is, well, before we get to stoichiometry, we know about gases already based on what we discussed earlier. We know that um, gases that we talked about, we're going to assume that they behave as ideal gases. And if the conditions are not at STP, we can also convert whatever those conditions are to STP conditions and do the appropriate calculations when it comes to gases. Now, um, in gas stoichiometry, these are the main types of problems that you will encounter, um, and that's encapsulated in this diagram right here. Basically, you could be given some information about a particular gas in a reaction. Um, you could be given the volume, the mass in grams, or the number of molecules or atoms. But the point is that you need to convert each of these to the corresponding moles, all right? So in the case of volume, you may need to use the ideal gas equation. In the case of grams, then of course, you use the molar mass to convert to moles. And in the case of atoms or molecules, you know that there will be some involvement of Avogadro's number. In any case, you need to get the number of moles because based on the balanced equation, you can convert the moles of A to the moles of any other substance involved in the reaction, which would be represented by B. All right, so the conversion factor going from here to here is based on the mole ratio as given in the balanced equation, which again underscores the importance of having a balanced equation to begin with. Then, depending on how the question is worded, once you get the moles of the other substance B, then you may be asked to convert that to any one of these here, either the volume, the mass in grams, or the number of atoms of molecules. So this is basically what is involved in the vast majority of gas stoichiometric type of problems, or generally any type of stoichiometric type problems. So we're going to look at some examples where we do calculations involving converting from mole to volume. In other words, moles of one substance involved in a reaction, converting it to the volume of another substance involved, assuming that the other substance is a gas. And we're going to do a similar type approach where you're given a mass of one substance involved in the reaction and you're going to convert it to the volume of another substance, another gaseous substance involved in the reaction. Okay, so here's an example. It says here, what is the volume at STP that can be formed from 0.500 moles of potassium chloride? And they gave you the balance equation, all right? And of course, I would advise you that if you need to check to make sure that the equation is balanced, all right? If the equation is not balanced, then you have to go ahead and balance it. All right, so first thing I would do is start off with what we're given mathematically or numerically. And what we're given in this case is 0.500 moles of KClO3. All right. And then I would convert that to moles of oxygen because that's what you're trying to get the volume, so you need the moles of oxygen. And we can get that based on the fact that there's a 3-to-2 mole ratio between those two. So basically, I would represent that in this conversion factor where I would have 2 moles of potassium chlorate and 3 moles of oxygen. And then the final conversion here would be where I convert the moles of oxygen to grams of oxygen. So that's where the molar mass would come in. And that would be represented by 1 mole of oxygen down here and 32.00 grams of oxygen above. And of course, from here, you'll do your number crunching. So 0.5 times 3 divided by 2 times 32. And according to my, wait a minute, I think I did something wrong here. 0.5 times 3. Oh, I know what I did wrong. The question asked for the volume, not the mass of oxygen. So that means I need to erase this here. Sorry about that. So I need to convert to volume. Now, the important part here to answer this part here is in the fact that they gave you the conditions as STP conditions, right? So that means that, and we know this already, that under STP condition, 1 mole of a gas will occupy a volume of 22.4 liters, right? So let's do that calculation. 0.5 times 3 divided by 2 times 22.4. And according to my calculations, when rounded off to 3 sig figs, this gives you a final answer of 16.8 liters. Let me do that again just to be sure. 0.5 times 3 divided by 2 times 22.4. Yes, 16.8 liters of oxygen would be the final answer. All right? So basically, that's how that is done. Okay, so let's do another example. Now, this one is a bit more complicated because in the first place, you're not given the balance equation. So let's work that out first because you can't even do the math part without figuring out what the equation is. So the equation, of course, is based on the information given. The question says what volume of hydrogen collected at 30.0 degrees Celsius and 700 torr will be formed by reacting 50 grams of aluminum with hydrochloric acid. So basically, you have to identify what the reactants are, and that would be aluminum and hydrochloric acid. So we write down the formulas for those two on the left side, and then the products of the reaction, one of them would be hydrogen. And this begs the question, what would be the other product? Well, based on the information provided and based on our previous knowledge, we know that if hydrogen is formed, that means that the aluminum must have displaced hydrogen from HCl. And what that means, therefore, is that the aluminum will come together with the chlorine to form a compound. So we have to figure out what the formula for the compound is. And because we know that aluminum, let me do a little thing over here. Aluminum has a +3 charge, and chlorine has a -1 charge. Then we know that we're going to need 3 chloride ions. So therefore, the formula for aluminum chloride that will be formed will be AlCl3. All right, and then we have to balance the equation. So to balance this, we're going to need a 6 here, a 3 here, a 2 here, and a 2 here. All right, so that's what we have to start off with before we can do anything else. Okay, so question says that we are reacting 50.0 grams of aluminum with HCl. So the first thing I would do is convert this to moles. So 1 mole of aluminum would be at the top. And the molar mass. So let me look up the molar mass of aluminum. And according to my version of the periodic table here, the molar mass of aluminum is 26.98 grams. So that would go down here, 26.98 grams of aluminum. And then I will multiply this by the mole ratio between the hydrogen and the aluminum based on the balanced equation. And you'll see that there's a 3 here as a coefficient for hydrogen, and there's a 2 here, which is a coefficient for aluminum. So here you're going to have 3 moles of H2 above and 2 moles of aluminum below. Then, so that would give you the moles of hydrogen. So let's work that out first. So that's 50 divided by 26.98 times 3 divided by 2. And according to my calculations, this works out to be equal to 2.78 moles of hydrogen. Okay, so the next step is to find out the volume. And to find the volume, we would use this equation that we met before. PV is equal to nRT. What the question is asking for is the volume, which is equal to N times RT over P. And then we plug in the values. The first of which is what we just calculated here, 2.78 moles. Whoops, sorry about that. Times R, which is always going to be 0.0821 liters, atmospheres over mole Kelvin, times the temperature. What's the temperature? Well, the question says 30 degrees, but remember, we have to convert that to Kelvin in order to use the ideal gas equation. So 30 plus 273, and that would be equal to 303 Kelvin, all divided by the pressure. Now, they gave you the pressure in torr, 700 torr. But we have to convert that to atmospheres. And if you recall, the relationship between the torr unit and the atmosphere unit is 760 torr equal to 1 atmosphere. All right? And then we work that out. So 2.78 times 0.0821 times 303 equals that. Then we divide it by 700 divided by 760. And according to my calculations, this works out to be equal to 75, round out to 366. So that's 75.1. And the units will be liters. So let me just show you how we get that units. The torrs will cancel, the atmospheres will cancel, the kelvins will cancel, and the moles will cancel. So the final unit here would be the liter unit here, so liters. And this would be the final answer, all right? Okay, so that's basically how that particular example is done. All right, now when it comes to volume calculations, this can be relatively simple or a bit more challenging depending on how the question is worded. Now, if the conditions are the same for all the gases, then the volume relationships will be the same as the mole relationships. And therefore, if you have the balanced equation, then that makes life very easy, all right, in terms of doing problems involving volume relationships. So for example, if you have this reaction here, which is basically made up of all gases, products and reactants, right? Hydrogen plus chlorine gives you hydrogen chloride. You see that the ratio between them in terms of moles is 1 to 1 to 2 respectively. But under STP conditions, we know that 1 mole of any gas occupies a volume of 22.4 liters, right? So basically, the volume relationships can be expressed as you see there, 22.4 liters of hydrogen reacting with 22.4 liters of chlorine to give you 2 times 22.4 liters of hydrogen chloride. So therefore, when it comes to volume relationships, and it doesn't matter what the volume units are, it's a 1 to 1 to 2 relationship in this reaction. So you can express a relationship as 1 liter of hydrogen reacting with 1 liter of chlorine to form 2 liters of HCl, or you could use the same ratio expressed in milliliters, expressed in gallons. It doesn't really matter what the volume units are. They will be proportional as described by the coefficients of the different substances involved in the gaseous reaction. All right. So we could simply apply this idea to this particular problem. Now, this problem talks about sorry about that, talks about the reaction between nitrogen and hydrogen to form ammonia. And it gives you the volume of hydrogen and is asking what the volume of nitrogen will be. So again, the first thing you have to do is write down the balanced equation, which would be, in this case, N2 plus H2 to form NH3. And of course, we have to balance it. So we're going to need a 3 here and a 2 here. All right. And the question gives you 600 milliliters of hydrogen, and you have to find the volume of nitrogen that will react with it. So here, the conversion factor that we excuse me, that we're going to have here is going to be based on the coefficients in the balanced equation, and that would be 3 milliliters of hydrogen reacting with 1 milliliter of nitrogen. All right? And of course, this will cancel with this. And when you work this out, you're going to get 200 mils of N2. And that's basically how that is done. All right? Okay, so that's how that type of calculation is carried out. And this only works if the conditions are the same for all the gases involved. Now, if the conditions are different, then you'd have to do a different type of process where you'd have to use the ideal gas equation. So what I'm going to do is search for a problem of that type so that you'll be able to do that type of problem. So I'm going to go to Google and look for gas stoichiometry problems. And let me see if I can find an example. So let me go to the first link right here. Okay, let me see what this question, what he says. Okay. Let me try to find a good one. I'm trying to find one where you go from gas to gas. Let me see, 13.5 grams, 29%. Okay, let me see. Okay, here's one. Here's a nice one. Let me go back to PowerPoint. And what I'm going to do here is create a new slide. And I'm going to paste the question here. Okay, so let me just make some space here so I can write the solution below. So here's a question. It gives you 45.0 liters of natural gas, which is essentially methane, and it undergoes complete combustion at 730 millimeters mercury and 20 degrees. How many grams of each product are formed? So of course, the first thing we need to do is write down a balanced equation for this particular problem, for this question. So one of the reactants would be methane, CH4. And as we all know, what is involved in combustion is that it will react with oxygen from the air to form carbon dioxide and H2O. Then we have to balance it. So to balance it, we're going to need a 2 here and that would make that 4 oxygens. So that means we need a 2 here to make that 4 oxygens. So that's what we need first. Okay, so now that we have the balance equation, it gives you 45.0 liters of methane, right? And it says it undergoes complete combustion at 730 millimeters mercury. Sorry, methane, CH4. And 20 degrees Celsius. How many grams of each product are formed? Now, what I'm going to do here is take the liberty of changing. Well, let me not do that. Okay, let me just work with the question as it is. All right, so the first thing I would do is try to find the moles, right? Now, how do we find the moles? Well, they gave us the volume, they gave us the millimeters of mercury, and they gave us the temperature. So that means that you'd have to use the ideal gas equation to find the moles. So N would be equal to PV over RT, all right? So that would be equal to the pressure, which is 730 millimeters mercury, which you have to convert to atmospheres. 1 atmosphere over 760 millimeters mercury times the volume, which is 45.0 liters, all divided by R, which is 0.0821 liters, atmospheres, over mole Kelvin, times the temperature, which is 20 degrees, which is the same thing as 293 Kelvin. And then we work out what this would give. So let me just do my number crunching here. So that would be 730 divided by 760 times 45.0 divided by 0.0821 times 293. And when I round this off to 3 sig figs, I'm going to get a relatively large number. Let me check this again. This looks kind of huge. 730 times 45 equals that divided by 0.0821 equals that divided by 293. Okay, I knew something was wrong. So according to my calculation, this works out to be equal to 1.37 times 10 to the 3. And the units here would be moles, all right? Because what's going to happen is that the Kelvin units will cancel here, atmospheres will cancel here and here, liters will cancel here and here, millimeters of mercury will cancel here and here. So the final unit remaining would be 1 over the mole here, which works out to be the mole unit here, all right? Okay, so that's basically how we get the moles. But we're not finished yet because the question is asking for how many grams of each product. I'm just going to show the calculation for one of the products and you should be able to figure out for the other because there are 2 products. One is carbon dioxide and the other one is water. So in the case of the carbon dioxide, it is 1.37 times 10 to the 3 moles of CO2, and then we multiply that by the mole ratio between the carbon dioxide. Actually, this should be methane, not carbon dioxide. So CH4 here. So basically, it's a 1-to-1 mole ratio between the methane and the carbon dioxide. So the answer here is going to be equal to 1.37 times 10 to the 3 moles of CO2, moles of CO2. And that's how you get that. And you should be able to by now to determine the moles of the other product, which is water. I won't go through that. I'll leave that for you to work out. If you have any problems with that, then let me know. All right, let's see what next. Oh, so the only final thing we need to talk about is the difference between real gases and ideal gases. So for this chapter, we have been assuming that gases behave in an ideal fashion. What do we mean by that? Well, just to remind you, an ideal gas is one that obeys all the gas laws that we discussed. So, Boyle's law, Charles' law, Avogadro's law, Dalton's law, the ideal gas law. Basically, all ideal gases obey all the laws that we were discussing before. But if you want to look at it at the microscopic level in terms of how the particles behave, there are two main characteristics of ideal gases. One is that the size or volume of the particles are effectively zero compared to the volume of the entire gas. All right? So that's one characteristic of an ideal gas. Another characteristic of an ideal gas is that there are no intermolecular forces between the particles of the ideal gas. All right? So those are the two um, properties of ideal gases at the microscopic level. One, the volume of the gas particles are effectively zero compared to the container that they're in. And two, there are no intermolecular forces between the gas particles. All right? Now, in the case of real gases, that's not the case, right? Um, so the behavior of real gases deviate from ideal gases for two reasons. One, in the real gas, the volume size is not zero compared to the container of the gas. And two, there are actually intermolecular forces that exist between the gas particles. And therefore, this would also have an effect on how real gases behave differently compared to ideal gases. All right. So let me just say here that even though that is true, it is possible to alter conditions such that real gases behave as ideal gases. And the two conditions are that if the temperature is high, for the gas, and if the pressure is low, then real gases will behave approximately the same, whoops, approximately the same as ideal gases. All right? So if you want to make a real gas behave like an ideal gas, you need to elevate the temperature and lower the pressure. And then the real gas will behave more and more like an ideal gas, and therefore will more likely obey the laws that we were discussing. Okay, so that basically represents the end of this chapter. So until next time.